Picture this. An astronaut lands on a planet. He's only there for a few hours, grabs some samples, looks around, maybe complains about the water levels, astronaut things. He gets back in his spaceship and finds out 23 years have passed back home. Not 23 years later, the movie skips ahead. No, for him, it was 3 hours. For everyone on Earth, it was 23 years. His kids grew up, got older than him actually, while he was gone for an afternoon. This isn't made up. This is the actual math from the movie Interstellar. And this is the wild part. It's based on real physics. Real, tested, GPS satellites use this every single day physics. So today we're going to figure out how that's even possible. And I promise, no physics degree required. If you can tell time on a clock, you can understand this by the end of the video. But here's what I really want to know. For those 3 hours, what was actually happening to him? His body, his heartbeat, his own sense of time, and even something as simple as the watch on his wrist. Hang on to that question. We're coming back to it. Quick question before we go anywhere. What is time? Go ahead, try to define it without using the word time. Kind of hard, right? Most people have never actually had to answer that. Here's the surprisingly simple answer. Time is just counting things that repeat. That's it. That's the whole secret grown-ups don't tell you. Look at any clock ever made in all of human history. Every single one does the exact same trick. Find something that happens over and over at a steady pace. Count it. Call that time. A pendulum clock counts swings. A wristwatch has a tiny quartz crystal buzzing about 32,000 times a second. Counts buzzes. The fanciest atomic clocks on Earth count an atom flickering over 9 billion times a second. Different speeds, same trick. Pick something repetitive, count it, call it time. Which means, time isn't really a thing floating around us. It's a count. And counts can behave in some pretty weird ways, as we're about to find out. Here's the one weird rule you need to know. And once you know it, the rest of this video makes sense. Light always travels at the exact same speed. Always. No exceptions. It can't speed up. It can't slow down. Doesn't matter who's watching it or how fast they're moving. Compare that to literally anything else. Throw a ball forward while you're riding a bike, and it flies faster than if you threw it while standing still. Your bike speed adds onto the ball's speed. Normal stuff. Light doesn't play by that rule, ever. It's the one true speed limit of the universe, and it never budges. Keep that rule in your back pocket. We're about to break physics with it. Let's break this into tiny steps. No step here is hard on its own. Picture this. You're on a train, holding a flashlight. You point it straight up. It hits a mirror on the ceiling and bounces straight back down to your hand. Up, then down. That's one tick of our flashlight clock. To you, sitting on the train, the light just went up and came straight back down. A straight line. Simple. Now picture your friend standing outside on the platform, watching your train zoom past. Your friend can also see the light bouncing inside. But here's the thing. While that light was going up and coming back down, the train was also moving forward. So your friend doesn't see a straight up and down line. They see the light go up and forward, then down and forward. It looks like a little triangle shape instead of a straight line. And here's the key part. A triangle shape is a longer path than a straight line. That's just true. It's like the difference between walking straight across a room versus walking there on a diagonal. The diagonal way is longer. So here's the puzzle. Your friend is watching the exact same light, doing the exact same one tick, but covering a longer path than you did. Now bring back the one rule from a moment ago. Light can never speed up, not even a little, not for anyone. So if the light has to cover a longer path, and it's not allowed to go faster, the only thing left that can change is how long the trip takes. That means your friend has to measure more time passing for that one tick compared to you, which means, from your friend's point of view, your clock on the train is running slow. And nobody did anything wrong here. Nobody's watch is broken. This is just what happens whenever something moves. Its clock runs a little slow, but only from the point of view of someone who isn't moving with it. That's the whole trick, start to finish. Moving fast slows your clock down, not because anything breaks, but because light refuses to speed up, so time has to bend instead. Speed isn't the only thing that messes with time. Gravity does it too. And it's the gravity version that's actually behind Miller's planet. Big heavy objects, planets, stars, black holes, bend the space around them. You've probably seen the classic picture. A heavy ball sitting on a stretchy trampoline sheet, making a dip that other balls roll toward. Here's the part almost nobody mentions. That same bending doesn't just warp space, it warps time right along with it. The stronger the gravity, the slower time ticks there, compared to somewhere with weaker gravity. Same exact logic as the flashlight game. Light still can't speed up, so if gravity stretches out the space light has to travel through, time has to stretch too, to make room for it. Miller's planet, from the movie Interstellar, sits ridiculously close to a black hole called Gargantua. And black holes are the heavyweight champions of gravity. Gargantua has the mass of about 100 million suns, crammed down into essentially a point. That close to that much gravity, time doesn't just slow down a little. It slows down dramatically. 1 hour there, 7 years back on Earth. Not 21, 7. Yes, we double-checked. Physics is picky like that. Remember that question from the very beginning? What was actually happening to the astronaut's body, and even his watch, the whole time? This is where we finally answer it. Everyone stops the story here. Whoa! Gravity slows time. Cool. Black holes are wild. Moving on. But here's the question basically nobody asks. What happens to the astronaut's body and every object he's carrying, like the watch on his wrist, while all this is going on? Because your body isn't just carrying a wristwatch. Your body is a clock. Actually, a whole bunch of clocks stacked on top of each other. Deep in your brain, there's a tiny cluster of cells called the suprachiasmatic nucleus. Say that 5 times fast. Or don't. Nobody will judge you for just calling it the SCN. The SCN is basically your body's built-in alarm clock. It watches for light coming in through your eyes, and based on that, tells your body when to release melatonin, the get sleepy chemical, and when to release cortisol, the wake up, let's go chemical. That's why you get tired at night and alert in the morning, and why jet lag feels so miserable. Your SCN's clock and the actual local time get out of sync, and your whole body throws a small tantrum about it. Your heartbeat is a clock too. So is your breathing. So is how fast your cells divide and repair themselves. You are, biologically, a walking pile of repeating rhythms, which, remember earlier, a repeating rhythm is exactly what a clock is. Here's the connection. If gravity can slow down a pendulum, a quartz watch, an atomic clock, and a beam of light bouncing between mirrors, there's no reason it would politely skip your heartbeat, or your sleep cycle, or literally any biological rhythm your body runs on. Gravity doesn't care whether a clock is made of metal or made of meat. If it repeats, gravity can slow it down. Which means on Miller's planet, it's not just the astronauts' watches running slow compared to Earth. It's their actual hearts, their actual cells, their actual sleep-wake cycles. All of it, dragged down together by the same gravity at the same rate. Here's the twist that should genuinely creep you out a bit. The astronauts never feel any of this happening. Stand on Miller's planet for that 1 hour. Your heart still feels like it's beating at a totally normal pace. You still get hungry on schedule. You still feel sleepy at the right time. Every clock inside you agrees perfectly with every other clock inside you. Why? Because there's no secret, real, universal clock hidden somewhere in the cosmos that your body could accidentally fall behind on. There's no correct speed that time is supposed to move at. Your pulse doesn't check in with some master stopwatch floating in space. It only ever compares itself to whatever's standing right next to it. Gravity doesn't grab your wristwatch and leave your body alone. It grabs everything: your watch, your heartbeat, your hunger, your sleepiness, and drags it all down together in perfect sync with itself. And totally out of sync with anyone standing somewhere with weaker gravity. So when Cooper checks his messages and finds 23 years have gone by, nothing sped up back on Earth. Nothing slowed down for him either. 2 sets of clocks, his body included, each one working completely normally from the inside. They just happened to be standing in very different amounts of gravity. Let's circle back to that question from earlier. Is there some real time ticking away somewhere in the background of the universe that everything else is either keeping up with or falling behind on? Nope. Turns out there isn't one. There's just clocks, pendulums, atoms, light beams, heartbeats, sleepy brains, each one faithfully counting its own repeats wherever it happens to be standing, agreeing perfectly with itself, quietly drifting from everyone else's. Nobody's late, nobody's early. There's just wherever you are and however fast time happens to move. There. Quick reality check before you think this is all just movie magic. This is measured, everyday, real-world stuff. GPS satellites orbit Earth fast enough and far enough from Earth's gravity that their clocks tick at a very slightly different rate than clocks down here. If engineers didn't correct for that math every single day, GPS would drift off by miles within hours. Your phone's little blue dot would basically be lying to you by lunchtime. So the same effect that makes Miller's planet dramatic in a movie is the same effect quietly keeping your Maps app accurate right now. So next time someone tells you, time flies, or I don't have enough time today, technically, they're more right than they know. Time really does move at different speeds for different people, depending on where they're standing. You're not running late. You're just standing somewhere slightly different in time than everyone else. If your brain feels pleasantly scrambled right now, good. That's the whole point of this channel. Subscribe, because next time we're going somewhere completely different. On this channel, literally nothing is off the table.